So there was some interest in seeing a solution to the blackjack problem. So based on where I started out last week, I went ahead and finished up my solution. So inside the loop here, I've zeroed out all the cards to begin with, set card 1 to a random number based on the number of cards. And then inside this loop, I'm checking to see what cards have been assigned yet. So if card 2 hasn't been assigned, I'm going to go ahead and assign card 2. And we'll go through. So that'll have the effect of assigning one card at a time from the remaining cards. And then for each one, I need to calculate the score and display the cards in my hand. So you'll notice I'm not adding to the score for an ace, because an ace is a unique card that can have a different value. It can be either a 1 or an 11. So since that value can actually change based on the other cards in my hand, I'm not going to set that value to either 1 or 11 yet. Then if my card value is less than 10, not an ace, but it's less than 10, I'm going to just add the numeric value of my card. Otherwise, I'll add 10 because I know the remaining cards are all going to be worth 10, and that'll be a 10, a jack, a queen, or a king. And just in case something really screwy happens, I put a question mark in there for an invalid card selection. And then I copied that code and used the same code for card number 2. Then for card number 3, there's a possibility that it won't have been assigned yet. So if it hasn't been assigned, I'm just going to skip all the rest of this. But if it has, I use the same code that I used for card 1 and 2. And then I'm going to display my score. So I already displayed my hand. And here's where I figure out what my ace or aces are going to be valued at. So if aces times the high value, 11, plus the score is going to be greater than a blackjack, I don't want to score it as them all as 11, right? So instead, I'll score them as 1 and add 1 to score, subtract 1 from aces. Now, however many aces I had before, I have 1 less ace. Multiply the remaining number of aces by 11 and see if that's greater than blackjack. As long as I end up with something that's greater than blackjack. Oh, and actually I figured out that there was another problem if I'm already over blackjack. So if I have an ace and my score is over blackjack, then I go keep looping here. Then I calculate my actual score here. Score equals score plus aces times ace high value. So if I still have anything left in aces, I'm going to count all of those aces as 11s. Obviously, there's only going to be 1 if there are any. But if it's 0, then that gets zeroed out, and I don't add anything to the score. If I'm still over the blackjack amount, which is 21, I report my score as busted. Then I have the hit or stand, which is going to go back and deal another card. Then I have the play again, which is going to start over and deal all the cards again. So let's run this real quick. So 2 7s is a 14. I'm going to hit on that. Whoops. Now I've got 3 7s, which is 21, so I'll stand. There's really no winning or losing other than going bust. I'm going to play again. 2 and a 5 is 7. I'm going to hit. Plus an 8 is 15. I'm going to hit. Now I'm busted. So now if I say don't play again, I'm going to report how many hands I played, how many times I busted, and my high score. Just for grins, I thought I would go back and see how much complexity I added to the project by changing it from the book. And it turns out having to have the code to interpret what the user entered is actually going to make it more complex. So the code you did was less complex, even though you had the random number generator in there, than you would have had to put in to interpret your code, allowing the user to enter a character value and then interpret that as a card. So in addition to the other code that we had, here's the code to enter your own card instead of getting a card from the random number generator. So let's run that, take a look at how that works. So this time I'm entering a card. I can enter any card I want to. So let's enter an ace. All right, with one ace, my score is 11. So let's hit, put another ace in, now it's 12. Hit again. Third ace will make it 13. Hit again. Fourth ace would make it 14. And if I hit again and get a 6, I've got a score of 20. And again, if I stop playing, I got the played, number of times busted, and high score. So what we're going to learn soon, though, is there are other tools that we can use that can simplify some of this. Oh, and I also went in and I did a version with a dealer. So So we get the dealer's cards. Basically, I copied everything for the user's hand with the random numbers and stuff, except for the dealer. Instead of asking if I want to hit or stand, for the dealer, I make him stand if his score is 17 or greater, or if I've dealt him 5 cards. So that's the dealer section there. It's exactly the same as the player section, except I've got a separate set of variables to hold on to the dealer information. So now if we play, I've got a score of 19. I'm going to stand. The dealer got 17, so I won. Play again. I've got 13. I'm going to hit. Uh-oh. Looks like there's a bug. No?
No, you just got a king.
I just got an ace, so it scored as 1 instead of 11. So I've still got 13. So I hit again. Oh, now I'm busted. Dealer had 2 9s and he won. So it makes it a little bit more fun. You can actually tell whether you're winning or not. And it gives us a little more information that we can display at the end. When I say no, don't play again, I've got the number of times I played, the number of times I busted, and my win and loss record. Still, that's kind of complicated, all of that stuff in there. Having to test each of those separately. So, pretty soon we're going to learn how to do arrays. Arrays allow us to reference multiple variables with the same name. So let's see how that changes my program. So now I have a card array and a dealer array. And I only have to have a loop for one card at a time, but I don't have to test each of the 5 different cards in a separate set of code, because an array lets you refer to it by a standardized name. And so now I have all of the cards, all 5 cards, in a for loop. And if I haven't gotten a card yet, I just break out of my for loop. So you can see that makes the code considerably shorter. So instead of 172 lines, we've got 193 lines. And I did one more version, just vision of things to come, functions. And this time, instead of figuring out what my card does in line inside my code, I call the decode card function, and it's the same function whether I'm using the dealer card or the user card. And that's going to tell me how much to score it, what my symbol is going to be, and whether it's an ace or not. So that version actually reduces our total lines a little bit more to 187. I almost forgot to pass out the roll sheet. Any questions about any of that? All right, let's go on to chapter 4. Yes? Okay.
I actually came up with, my solution was quite a bit different than yours.
Okay.
I originally did one that was like yours.
Yes.
And I had, card 1, 2, 3, 4, 5. But then I realized I could shorten the code a lot if I just kept randomizing card and printing the same card. So I just have one variable for card.
Okay.
You can bring up my code if you want.
What about as you deal each card out as you're building your hand?
It prints it as you go.
Okay.
And randomizes it again after that.
And how did you deal with aces counting either 1 or 11?
I kept track of aces. Kind of like what you did, but
okay.
If I did a while statement, find it. Basically, I don't see it, but basically what I did is I kept track of aces, and there were aces, and then I did a Boolean statement for if it was aces was greater than 0.
Okay.
And total was greater than 21, then would subtract 10 from the total.
I see. Okay. Well.
And then instead of doing a case for each one, I did a case for aces, a case for jacks, a case for queens, a case for kings. And I used the default, and I just put the card in the default and added the sum of the card to the total.
Well, that sounds like could be another solution that works. So I like to say there's at least as many possible solutions as there are solutions submitted. So there's always another way to do it, and depending on what you're going for, that could very well be the best solution for you. So if it works and gives the right answers, then it's a good solution. All right, let's talk about Chapter 4. Procedural abstraction and functions that return a value. So when we are creating a program, one of the things they like us to do, we said our set of instructions is called an algorithm. But one of the ways to design an algorithm is to start with a set of tasks that we can consolidate. And each of those tasks may have a number of subtasks. So if we're saying one of our tasks is to figure out what the value of this card is, we could say that has a series of subtasks that are, well, is it an ACE? How are we going to treat that a special way? Is it a numeric card, 2 to 9? We can just add to our score. Is it a face card, and so on. So we call that method the top-down design method, or stepwise refinement, or sometimes divide and conquer. And so those smaller subtasks can actually be written as separate pieces of our program. And in some languages, we call those subprograms, subroutines, procedures, methods. In C++, all of those are called functions. And so to begin with, we have some functions that have been predefined for us. For example, we did our random number functions, srand and rand. Those are predefined functions that do something that we want to be able to do. It takes an argument. This value that we put in here is actually a number that is the argument to that function. It happens to come from another function that we called time. And the time function returns the number of seconds that have passed since January 1st, or midnight January 1st, 1970. And the srand function is going to use that number as its seed for the series of random numbers it's going to give us when we call the rand function. The rand function actually has an argument list, but its argument list happens to be empty. And the rand function is going to return a value. We learned when we started looking at our, we learned that that value that it's going to return is an integer. And when we looked forward to find the rand function, we learned that it's guaranteed to be at least 32,767. It's actually going to be rand max, which is defined in the CSTDLIB library, which we had to include in order to use the rand function. So that value that it returns is going to be an integer in the proper range. We use the modulus to make it fall into the range that we need it for. In our case, 13, which means it'll be between 0 and 12. We then added 1 because we wanted our range to be between 1 and 13 instead. That was a function call, or function invocation. And there's lots of predefined functions that we can use in that way. For example, display 4.1 uses the CMath library and calls the function square root, sqrt, which will give us the square root of the argument that we passed as its returned value. I've been calling these libraries. Older versions of C and C++ used header files. A header file is just a file that has some code in it that may call other files or include other files. Changing them to be libraries just made it a little bit simpler and made the code that's in them a little more abstract, so that people are not as interested or not as concerned with looking at what code is actually in there as knowing what the library is and what it does. This book shows you some of the predefined functions that are in CMath. Actually, some of them are in CMath, and some of them are in CSTD-LIB, C standard library. Square root, power, absolute value. There's actually 3 different absolute values because those were created before they started standardizing things and doing overloaded function calls. What actually happens is the contents of that library get copied into your code at that point by the preprocessor. Not that it really makes any difference. And then page 188 and 189 talk about the random number generator that we already used for our homework. Then they talk a little bit more about typecasting and how dividing one integer by another produces integer division. So we can explicitly change the data type for a value by using the static cast. And that will allow us to, if we had an integer division, but we didn't want to produce an integer division. We wanted to actually change and use doubles, and needed that to be explicit. So for some reason, this really needed to be defined as an integer rather than a literal constant in the code. We could call the static cast and cast that to a floating point value instead. It's only going to apply to the value that's inside the parentheses. So if we did it like this, that would really defeat the purpose. Because if we did it like that, we would still be dividing 9 by 5, which is an integer division, and we wouldn't get the value we wanted. If you go out and look at code on the internet, you may occasionally see something that looks like this, using the name of a data type as if it were a function. That's the way they used to static cast a value. But better to do it a new way in case they ever discontinue that version of the static cast. All right, so we have some self-test exercises on page 192. Let's figure out what some of those are going to do. Mr. Brantley, in number 1, let's do the fabs minus 3.0. Okay, it will be 3.0 because it's going to return a double. So we want to make sure that when you write your answer to a question, you represent it as the right type of data. So 3.0. All right. Ms. Hernandez, how about PAL 3.0, comma 2 all over 2.0?
All over 2.0.
Sorry?
All over 2.0.
Right. Okay, 4.5. And Mr. Rahim, can you do the one in the bottom right-hand corner of that table, square root PAL 3, comma 2?
Two, no. Three.
Okay, so again, square root is going to return a double, so it's going to be 3.0. So 3 squared would be 9.0. Square root of 9.0 would be 3.0. Yes?
So just saying 3 would be wrong. So
Well,
3 would be 3.0.
3 would be an integer, which technically would be wrong. So 3.0 would be the correct answer. All right? Mr. Gear, let's convert a couple of expressions in number 2. Square root of x plus y would be what in C++?
SQRT, parentheses, x plus y, parentheses.
Okay. And Ms. Hargrove, how about minus b plus the square root of b squared minus 4ac over 2a?
Much easier when you write it down. Minus B, parentheses minus B,
Okay.
plus parentheses, square root, parentheses, I think another parentheses, power, parentheses, B times 2, parentheses, minus 4 times A times C, parentheses, close. Right? Oh, and then slash 2A over 2A.
Okay. So our parentheses are a little off here. We need 1, 2, 3, 4. And we need it to be 2 times A. And we should probably put that part in parentheses as well. And B squared would actually be B times B, so we could have just done that. But, other than that, yes, that's correct. All right, let's take a short break, and we'll continue in about 5, 6 minutes.